Hello friends, welcome to this channel. Here we are going to look at today's daily challenge problem, put marbles in bags. This problem is marked hard by leetcode. Indeed, it's not very straightforward, but if you realize or digest the key points, then the problem will be rather straightforward. So here we are given key bags, and also we are given a list of weights, right? So we want to cut this weights into key sublists, right? And then the scope of computation will be the following, right? So for a sub-array, the corresponding cost will be the first weight plus the last weight within that sublist, right? So we want to find the difference between the maximum and minimum scores among marble distributions. Here, let's quickly look at one example, example 1. So we want to partition this original array into two sublists. So this is the one partition, right? This is another one. So for the first one, if you compute the cost, so here the first one has length 1. So the first element and the last element are the same, both are 1. So we have 2. And for the second part, so we have 3 and 1 as the two ends. So you get 4, right? So 2 plus 4, that is 6. And for the second partition, so for the first sublist, the first and the two ends are 1, 3, right? You get 4. And for this one, the two ends is 5 and 1, you get 6. So then you total is 10. So the difference will be 4. So that's the understanding of the example 1. So the constraints are the following. So here I'm going to focus on the first one. So the length can be as long as 10 to the power 5th, which means that we need to think of time complexity when we design a solution. The second one is also somewhat important because the weights are positive, right? So with that said, let's quickly go over the major points. So there are 2 points you need to realize or digest so that you can easily do the problem. First is that when we split subarray between indices I and I plus 1, then we create a boundary where width I and width I plus 1 will be the ends of their respective bags. Therefore, both the two values will contribute to the final cost. So this is the one point. It's very easy to understand, right? So for example, you have a weight at some place, and then up to this weight I, right? So this will be one end, and then weight I plus 1 will be the start of the next one. So this score will be in the cost of the previous one, and this score will be cost in the next one. So overall, so Wi and Wi plus 1 are part of the final cost of the partition, right? See. So this is the one part. The second part is that you need to notice that we're not computing the maximum or minimum scores explicitly, though we can, right? So we are interested in the difference. So this actually simplifies the problem. So with that said, basically for key bags, right, we want to partition the original list into key sublist. So we need key minus 1 cutting points, right? So to maximize the score, we want to cut at positions that results in the highest boundary costs. I mean, for those sums, right? And to minimize the score, we want to cut at positions where the lowest boundary cost occur, right? So here are the algorithm. So first we can handle the edge case where when k is 1. So if k is 1, we don't need a partition, right? So the largest cost and the smallest cost will be the same. We just need to return 0. And then for each other potential cutting points between adjacent elements, so we calculate the pair sum. So that is weight I plus weight I plus 1. And then we can sort those pair sums. So for minimum score, we use the k minus 1 smallest pair sums. And for maximum score, we use the k minus 1 largest pair sums. Notice that these pair sums may not be the maximum cut score or cut cost. it's only occurs when the first partition or last partition just have one element, right? So you need to add the two ends, the original array, this one and this one. That's a difference between the boundary score accumulation and the maximum card score, right? But what we are focusing on is the difference. So with that said, I guess you should be able to digest the main logic. Now let's look at the coding. It turns out the coding is very short, right? So here, let me first, if k is 1, right? We just need to return 0. This is rather straightforward. And now let's have the pair sums. So basically, we need to have k minus 1 positions, right? But if the weights have length n, then we will have n minus 1 positions of cards. But we can have all those cards. We can get all the n minus 1 pair sums, and then we do sorting. So let's do it. So for I in range, so up to this weights minus 1, I guess that will be. So then what we want to do? So the pair sums. So pair sums. So append. So here what we want? Let me change this one to be W, just for ease of writing. So what we want to add is Wi plus Wi plus 1. So here I read a length W minus 1. So here, let's assume the length is n, right? So the largest I will be this one. Then I plus 1, the largest I plus 1 will be n minus 1, right? It makes sense. So once we have this, when we done the job, now what we do? We do a in place sort, right? And then the score corresponding to the minimal score will be sum pair sums. So the first k minus 1, right? And then the max score will correspond to the sum of the last pair sums. So onwards. Notice that this mean score and the maximum score is not exactly the card cost or card score in this definition, but their difference will be the same because they are just missing two endpoints, right? If you add, say, weight 0 plus weight n minus 1, so I guess negative 1, right? So this will be the score, but I don't think we need to do this, right? So then what we want to do is to return the maximum score minus the mean score, right? So before we make comments, let's first test it. Yeah, it passes the test cases. Now let's look at the generic case. Yeah, it passes the generic case very fast. So here I want to make two comments. First one is temp complexity. So the temp complexity actually is from here, right? So because this is the linear and this is the linear temps logarithm, so the overall will be n logarithm n, right? I'll write like this, or you can just multiply and then put something like this. And the space complexity would be O of n, right? So because we use this list. So this is one comment. The second comment is the mean score and the maximum score via the score in the problem requirement, right? So here I can do some print. So yeah, let's look at example 1. So here you have mean score is 4 and maximum score is 8. But if you look at the explanation for this one, right? Because I didn't add the two ends, right? 1 and 1. If you add 1 and 1 in the mean score, there will be 6 corresponding to the smallest one. Similarly, if you add 1 and 1 in the maximum score, you will have 10. 10 minus 6 and 8 minus 4, they are the same. So now if you look at this one, example 2. So so the scores so for the mean score will be 4, and for the max score will also be 4 defined here. But if you use this, you add the two ends, the mean score and the max score will be, I guess, 1 plus 1, that is 2. 6 plus 3 plus 3, 6. It will be 8, right? In other words, we need to add two ends, that is 1 and 3, it will be 4, right? So in other words, in the sense of the problem statement, both the scores will be 8. But here, for the computation, we just need this two variables, right? That's the difference, right? So that's the difference by weight at 0, and weight and length weight minus 1. So that's the second comment. I guess with that said, that's about it for the current video. We have a playlist which contains more than, I guess, a lot of playlists. You can use those playlists to practice. Hopefully it will be of use to you. Thank you for watching.